Okay, so today we are going to discuss cosmic microwave background. We are going to begin discussing cosmic microwave background. Here is the outline. I'm going to discuss with you the sources of the temperature. This is going to be temperature anisotropy. Sources of temperature anisotropy. There are three different effects that enter the game. And then I will, give an idea of how you calculate this. How can you understand what's going on? And finally, we'll try to illustrate or give an idea of why cosmic microwave background is so sensitive to many things which you would like to know, which has to do both with the primordial perturbations, which we were discussing at length previously, and also the evolution of the universe after photon loss scattering. So to begin with, what do we have? We have in our universe density contrasts in the cosmic medium, in dark matter, in baryon photon component, baryon combination, etc. We also have gravitational potentials, gravitational perturbations of metric, and also we have velocities, right? Our fluid, our cosmic medium has certain velocity. So all these effects, all these properties affect the cosmic microwave background. So let's see how they do. So what we would like to understand is what is the temperature of photons coming to us from different directions in the sky. Okay, in the first place, let me write down the action for electromagnetic field, G mu nu G lambda rho, F mu lambda F nu rho, okay, where F d4x, where F is the standard d mu a nu minus d nu a mu, right? This is, in fact, a covariant quantity because, okay, it's two form. It's covariant quantity. It's tensor. Now, the first point is that we were considering metric which was ds squared equal to a squared at mu nu plus h mu nu dx mu dx nu. But in fact, if we plug this in here, the a factor will drop out, right? You immediately see that the square root of g is a to the fourth, whereas each of the inverse of these metrics contain 1 over a squared. Therefore, this a factor drops out, so what we can consider instead is the metric of this form, okay? Perturbations perturbed about the flat metric. So we will be talking about conformal quantities, conformal momenta, conformal frequency, etc. That's one point. The second point is that what we would like to calculate, we would like to calculate how the photon energy, what's the photon energy here once it was emitted at a certain energy, conformal energy, but that doesn't matter for us for the time being. What was its energy when it was, we know its energy was emitted, we want to know what this energy is today here. For that, how do we do that? We solve the equation for evolution of the photon, and if photon moves along x mu as a function of eta, then x mu here are eta and x, then the photon momentum is proportional to dx mu d lambda. You can introduce the affine parameter lambda in such a way that this is the photon momentum. For momentum, it's not velocity here. It's lambda is not s. It's not the time the interval along the trajectory, because the photon is massless, and therefore ds is equal to 0. It's just a parameter along the trajectory, and you choose it in such a way that this is the momentum. Now, as anybody else, photon obeys geodesic equation, which I write, which in general has this form: dp mu d lambda plus gamma mu lambda p lambda p nu equals 0. That's the general equation for a photon, plus you need the fact that this is null geodesic with ds squared equal to 0. And this tells you, among other things, how the photon frequency, how the photon energy P naught evolves as the photon travels, right? So let me say that P naught is d eta over d lambda, where eta is the time along the photon motion, world line. So, and let me write that dp naught over d lambda is dp naught d eta times d eta d lambda, which is p naught dp naught over d eta, and I use this equation here for mu equals 0, so that I get p naught dp naught d eta plus gamma 0 nu lambda p lambda p nu equals 0, okay? Or if I divide by p naught, here I get p naught, here I get p naught, and here I get times p naught. Okay? That's my equation that tells me how photon frequency evolves in time as the photon moves through the universe. Right, now let's do our calculation for scalar perturbations and tensor perturbations. Let's see what are the effects of scalars and tensors. So for scalar perturbations, we have metric scalar perturbations. We have the metric, which is in conformal Newtonian gauge, h naught naught is 1 plus 2 phi, hij is 1 minus 1 plus 2 psi in general times delta ij. And from that you immediately calculate, I mean, the point here is that this term is first order. If for trivial metric it's 0, okay, and here gammas are also first order. If I forget about the scale factor, which I did here, so these are 0th order things, whereas this one is first order and this one is first order. So we need to calculate the Christoffel symbols to the first order, and you'll do that straightforwardly. I don't think I have to calculate them, it's trivial. Gamma 0, 0, 0 is phi prime. To the leading order, gamma 0, 0 I, that's what I need, is di phi, and gamma ij 0 for this metric is delta ij times psi prime. where prime, as usual, denotes the derivative with respect to time, conformal time eta. Okay, that's scalar. For tensor perturbations, we have only hij, which is transverse traceless. So h. So what I'm writing here, I should write here g not and gij. I have non-trivial components, which are gij, which is minus delta ij plus hij minus hij transverse traceless. That's the only non-trivial components. All the rest is trivial. G naught is 1, G naught I is 0. So for tensor perturbations, we have gamma 0 ij is the only non-vanishing Christoffel symbol of interest, and it is equal to minus 1/2 of hij prime. Okay, I drop this notation. This is transverse traceless, but you understand that it's there. All right, so then we have this geodesic equation, which is now straightforward to write down explicitly. Right, so for scalar perturbations, we have from this equation that so nu and lambda could be either 0 or special. So we have dp naught over d eta is proportional to p naught, of course. So let me write down like this: 1 over p naught equals minus what's written on the right hand side. So gamma naught phi prime minus general. Okay, and okay, that's one thing. Then my nu can be spatial and lambda 0. Then pi over p naught is the direction of the motion of my photon, right? And I need it to the 0th order, since my gamma is first order. So it's just the direction the photon travels. And I have two of these terms, two cross terms with 0, either lambda or nu, and spatial the opposite. So I have 2 di phi times ni. I don't distinguish between upper and lower index I, as we agreed. And finally, you can have also nu and lambda equal to I and j, and therefore you use this Christoffel symbol gamma naught ij. And this gives me n squared, which is 1. So here I get also psi prime. Very simple geodesic equation, right? And this P naught is just the energy at the 0th order, right? So immediately you integrate this. You integrate this and use the following fact. You use the fact that phi prime plus ni di phi is nothing but the total derivative of phi evaluated as everything in here should be evaluated at the photon load line. So this is total derivative here, okay? Right, because dx over d eta is nothing but direction, momentum, okay? So let me write this thing here as minus 2 phi prime plus ni di phi, and plus phi prime minus psi prime. Okay? And this is time derivative of the photon frequency, photon energy. Okay, so finally I get the following thing. I get that the photon energy at us, 8 naught, in our place, minus photon energy at emission, and let me call it recombination, at R, is this integral divided by P naught, the unperturbed photon energy. It's this integral, right? And you integrate this thing here, since this is total derivative in time, this will give me minus 2 phi of eta naught minus eta phi of eta r, and the integral term. And the integral term is this, plus integral d eta phi prime minus psi prime. Okay? So that's how photon energy evolves, changes from emission to today. Okay? It's not the whole story yet, because I have to understand what was the energy of a photon when it was emitted, right, in my conformal Newtonian gauge. And there are two things. One is that my energy, my medium is in motion. It has certain velocity. And when I calculate temperature, it's temperature in local Lorentz frame, right? That's one thing. And another thing is that temperature is different in different places in my conformal Newtonian gauge, simply because there are perturbations in energy density and therefore perturbations in temperature. Okay, I have to account for that. So let omega be the frequency in local Lorentz frame. Okay. Now, what is the frequency in the? What is the energy? What is P naught? Right, P naught is energy in my chosen frame, which is the conformal Newtonian frame. Well, let me introduce the velocity v mu of the of my medium, right, which is dx mu over d eta. Right, this is the velocity of my medium, but this is conformal velocity. This is the physical velocity, and I need also, so this is, as we wrote, 1 minus phi, this is its zeroth component, 1 minus phi, and vi, which is a spatial component, right? That's what we did before, right? When we started to do this is perturbation. This is the velocity of my medium. Okay, I need also v mu, which is eta mu v nu. Sorry, g mu v nu, right? And this will give me 1 plus phi, since g mu is 1 plus 2 phi, 1 plus phi and minus vi. Minus because here I don't distinguish between upper and lower Latin index, and gij is minus delta ij. Okay, so that's my velocity. Why did I introduce that? Because I can write down the frequency in the locally Lorentz frame as V mu times P mu, right? In the locally Lorentz frame, V mu is 10000, and P mu is just the frequency of a photon in this frame, right? But the point is that this is an invariant, and therefore in the local Lorentz frame it's equal to frequency of emitted photon, and in my frame this gives me relation between this frequency and momentum. Okay, so it's equal to P naught 1 plus phi 1 plus phi, yes, minus VI PI, right, which is NI P naught. Okay? So that's how my frequency in the local Lorentz frame, which is just the temperature locally there, that's how it is related to the energy in the conformal Newtonian frame. Okay. All right. So from that, I find that P naught is, of course, omega minus minus omega times phi plus NIVI omega. Okay, to the leading order again. I mean, to the first order perturbations. Okay, good. So I now have related already the energy at emission, and I know, once I know energy at emission, I know energy which I receive. Okay? So I think I don't need that. Therefore, you plug this expression in here, both for our energy. We also move with respect to, may sit in a potential well, and we move with respect to the conformal Newtonian frame, and also for emission. This guy partially cancel out. These two guys partially cancel out because of this phi here. So all in all, what I get is that omega, which I measure in my reference frame, minus omega measured the energy as recombination, the energy of a photon emitted as recombination, divided by the omega, whatever it is, the average, the unperturbed photon frequency, equals minus phi at eta 0 plus phi at eta r minus VI and I at eta 0 plus VI and I at recombination, and the integral term, the integral phi prime minus psi prime d eta, which this integral is taken along the path of a photon. Okay? So that's basically it. Now we recognize that this term here tells me that if I am sitting in the potential well, then my received frequency will be slightly different from the frequency in the conformal Newtonian gauge on average. This term is the term which describes Doppler effect due to my motion, my velocity vi at the moment of receiving the photon. And we do have some velocity. This term is not zero. This term is there. It's a dipole component of cosmic microwave background. We do move with respect to the rest frame of CMB photons. But if I'm not interested in my own motion and my own gravitational potential, then these two terms are irrelevant. So I erase them. Okay. And all the rest is the intrinsic anisotropy of cosmic microwave background. Finally, I recall that frequency at recombination, omega r, is the frequency of a photon, but the average frequency, the unperturbed frequency, but there is also the contribution due to the fact that my temperature in my locally Lorentz frame is different because my energy density, because I have the perturbations in energy density. Okay? So, finally, I get the following formula for the energy or temperature, which is the same thing, since the change in energy is proportional to energy itself. My spectrum doesn't change. It was the Planckian spectrum. It will remain Planckian spectrum, modular redshift. So delta t, therefore, which is the difference between the delta t measured as a function of n minus n, let me explain, I'll explain in a second why this is minus n, but the delta t at minus n, where n is still the direction of photon motion. So minus n is the direction on the sky, right? Is equal to, it doesn't really matter, but anyhow. So it's equal to the following thing. It's equal to delta t over t, the delta t at write down over t, delta t over t at recombination. All right, this is simply due to the fact that this omega has this additional term here at recombination, delta t at recombination. Right, that's one thing. Another is that I have phi at recombination. That's here. Then I have vi and I at recombination. It's here. And finally, I have integral along the photon path phi prime minus psi prime d eta from eta recombination to today. Okay? So if I'm interested in the in the direction in the sky, then I change the sign here and I change the sign here. My photon moves towards me. Okay? Good. So that's it. That's basically the formula that relates temperature fluctuation we measure today here on the left-hand side with gravitational potential at recombination, with temperature perturbation at recombination, or let me rewrite this in slightly different form, which is, the same thing, but 1/4 of delta gamma, where delta gamma is delta rho gamma over rho gamma, right? And this is 4 times delta t over t. Since my rho gamma is t to the 4th. Okay? So it relates the temperature I see on the sky in the direction n to the potential. Of course, this potential should be calculated at x equal to minus n plus n times eta 0 minus eta recombination, right? At the point where the photon was emitted. And likewise here, velocity should be calculated at this point. It's not, I mean, it's the point where the photon has been emitted. Okay? Velocity, and also the fact that when the photon travels through the universe, the gravitational potential changed. Okay? So the first term here is called Sachs-Wolf effect, or Sachs-Wolf, probably. The second is Doppler, obviously. And the third one is integrated Sachs-Wolf effect. Right? So this is the entire thing here is Sachs-Wolf. This is Doppler. This is integrated Sachs-Wolf. Sachs-Wolf effect. Okay. So let me probably. This is so important formula that I should write it again. So delta t over t equals 1/4 of delta gamma plus phi minus ni vi plus integral phi prime minus psi prime d eta. The 0 to recombination. And so these are the three effects that contribute to the temperature of cosmic microwave background. Now for tensor modes, I can do the same thing, but for tensor modes everything is simpler because there is no delta gamma, neither phi. The only thing that remains there is the Christoffel. Okay? So for tensor modes, what you get is that delta t over t equals, let me make sure I have signed right, which is unimportant, but still plus 1/2 of integral hij prime. Remember that was the gamma, the minus gamma, 0 ij, that's the only term here, and ni and j, which come from here. Okay, I insert gamma here, integrate over along the photon world line from eta 0, eta recombination to eta 0, and that's the outcome. Okay. Now, the interpretation of all these terms is clear. The Sachs-Wolf effect has to do with the fact that you have, first of all, the energy density contrast, and therefore different temperature in different places. You are in gravitational potential, so the photon, if this gravitational potential is negative, then it means that you have potential well, and the photon has to climb this potential well. This is obviously clearly Doppler effect. If the photon moves from the direction n with velocity v, then you get, if this velocity is towards you, negative, then this term is positive, this is Doppler shift. Finally, this term accounts for the fact that if photon travels through the universe, it meets the potential well, it drops down the potential well, it gains energy, and if the gravitational potentials evolve in time, then it goes back at different value of the gravitational potential, so it climbs different slope. So altogether, it may gain or lose energy depending on whether the well became deeper or shallower as the photon travels through it, right? And this term is also known as integrated Sachs-Wolf. All right, so what then you do with this expression here? Well, that's basically it. You have to know what the various terms here are, and then you go and calculate the pattern of anisotropy, of temperature anisotropy in your background, in your cosmic microwave background. Good. Most of you, of course, know, but not for completeness, what people are doing with cosmic microwave background. The convenient way to analyze it is to say that if I have my temperature measured depending on n, then you decompose it in Fourier over sphere. So you decompose it in spherical harmonics, YLM of n times ALM. And if you assume that all these quantities here are Gaussian random variables, then, and they are, observationally, then these ALM are also Gaussian random variables, right? So experimentally, you calculate the sum of these. It should be independent of L. And theoretically, what you can do is to calculate ALM, A prime, L prime, M prime. Right? This averaging is the averaging over ensemble of the universes, right? This is the Gaussian random variable, meaning that you need to describe it properly. Theoretically, you need an ensemble, so it's an average over the ensemble of the universes, and being averaged over this ensemble should be equal to some constants that depends on L, and if everything is statistically isotropic, then of course your multiple numbers should be equal to each other. Okay? So these are famous CLs, which you calculate theoretically. Experimentally, you of course cannot do that because you don't have an ensemble of the universes. Instead, experimentally, you define CL as 1 over the complete number of harmonics with given L, sum over, it might be star, ALM modulo squared. Okay? Star because these y's usually have complex phases in them. All right, so experimentally you do that, theoretically you do this. Okay, so experimentally you have intrinsic uncertainty related to the fact that we have only one universe, and that's called cosmic variance, right? You have only 2L plus 1 variables with the same L. So if you consider them as members of ensemble, then you have 2L plus 1 members of an ensemble, not infinite number, and therefore you have statistical uncertainty related to the fact that you have only 2L plus 1 members of the ensemble. And let me show you the picture. You, of course, have seen it many times, but yet. To appreciate that, all these uncertainties, especially here and also here, are claimed to be cosmic variance. It's not that you have experimental uncertainty of this sort or systematic uncertainty in the experiment. It is just the fact that we are dealing with a single universe. Therefore, for octopole, say, L equal to 3, you have only, what is it, 7 harmonics, right? So your uncertainty is huge. It's square root of 7 over 7, right? 1 over square root of 7, which is big. So you can't actually do better than this. Once you proceed further to higher multiples, then of course this problem is less severe. Although it is severe, if you want to do statistical analysis, not just of these CLs, but if you want to study more intricate properties like non-Gaussianity, you want to study 3-point correlation function of the of ALMs, for example, or 4-point correlation function, then you need a lot more data. And the fact that you have finite amount of data, one universe, and only a handful of these harmonics, especially for low L, puts restrictions on what you can in principle do if you have, if you are considering finite number of multiples. And that often restricts the information that you can, in principle, dig out from this picture, from this figure. All right, so let me give you an idea of how you can analytically calculate the this curve. And let me just, for giving an idea, let me just calculate, or sketch a calculation of the multiples at low L, at small moment. Of course, you have to you should understand that there is an approximate relation between the angular scale theta and L, which is pi over L. Okay, roughly. So dipole would correspond to 90 degrees, 180 degrees, quadrupole would correspond to 90 degrees, etc. Quadrupole is L equal 2. Okay, so this is approximate relation which is similar to what you have for momentum in three-dimensional flat space and wavelength, right? So this is essentially Fourier decomposition on a sphere, and it's similar to Fourier decomposition in flat space. Okay, so that's why sometimes people show angular scale here, which is rough thing. It's not something exact, but the relationship is this one. Okay, it's just for understanding of where we are. So these are large angles, these are small angles. Okay, good. Now let's see how can we understand, how can we calculate the temperature anisotropy for Sachs-Wolfe. For example, this term here. Okay, forget about these two others. They are actually subdominant. We'll see why. So Sachs-Wolfe effect at large multiples. Large meaning L okay, large means L greater than roughly 50. Smaller than 50, sorry. Small multiples. Large angles, small multiples. Okay, roughly. I mean, of course, this is not, this is. Okay. So these are modes which remain super-horizon until recombination, essentially. We'll see that there is an approximate relation between L and momentum. And the relation is this, that L is momentum, the approximate relation is this, eta naught over eta recombination. Okay? Am I right? Let's see. No. Sorry. Sorry, it's wrong even. It's K is L over eta naught. That's the right expression here. Okay. So this is, of course, the dimensionality is now correct. That's basically the following thing. If you look at the mode of wavelength of inverse K, right, you see it at an angle. So this would correspond to the following. Lambda is 2 pi over K. Okay. That's on. Let me make it inverse, right? So 2 pi over K is 2 pi over L times eta naught. Okay. 1 over eta naught. Approximate relation here. Now, this is the wavelength. So this is the ratio of wavelength to the I'm talking about coordinate wavelengths and coordinate distances. To coordinate distance to recombination, right? So this is an angle. You see the wave at given momentum k, right? So that's the angle at which you see the mode of given momentum k. And here I have modulo 2, the angular scale inferred from this decomposition, okay? So basically, what I'm talking about is if my L is less than 50, this means that I'm talking about large angular scales for which K eta naught over the eta r is less than 1, right? Because eta naught over eta r is 50, so my L is, so that gives me K eta naught is less than, what I'm, sorry. K eta r is less than 1. That's correct statement, because then K is less than 1 over eta r, and this will says that L over eta naught is less than 1 over eta r, or L less than eta naught over eta r, and this is, as we discussed, is about 50. Okay, so let me say again. Let's consider the modes which are superhorizon at recombination epoch. Okay, these obey this relation that K eta r is less than 1. Okay, that was our condition that the mode is superhorizon, which means that K is less than 1 over eta r, and according to this approximate relation, L over eta naught is less than 1 over eta r, meaning that L is less than eta naught over eta r, which is 50. So if I'm talking about multiples less than 50, well, somewhat less than 50, then I'm talking about the modes which are superhorizon still at the recombination epoch. Good. Anyhow, for these modes, I have a relation that relates my initial perturbation. Remember, we called it zeta, to the term that stays in the integrated Sachs-Wolf effect. 1 over 4 delta gamma plus phi is some number, let me call it TSW, times zeta. Okay? And for this particular mode, this is called transfer function. This particular Sachs-Wolf transfer function, this transfer function is just a number, right? Remember, yesterday we calculated both and you can dig out this number from your notes. We calculated the gravitational potential and also the density contrast at recombination in the matter-dominated epoch for modes which stay superhorizon at the time, and these were just numbers. Remember this 2 over 5, etc. So it's just a number. Now, what I need to calculate this ALM is this expression here in the coordinate space. We were doing everything in momentum space, so in the coordinate space, this thing here in coordinate space is just integral of IKX, right? TSW in principle of K, and at eta recombination depends on the recombination epoch, the time zeta of K d3K. Now there are a few tricks you can use to, so what you have to do is to take this thing at x equal to n times eta naught minus eta recombination, which is essentially n times eta naught. Since recombination time is much smaller than the present time, you have to calculate this thing here at this coordinate x, right? Plug this into the inverse of this relation. ALM is integral YLM star of n delta t of n d omega. Okay, you have to take this thing here, plug into this expression here, integrate over angles, integrate over momenta. So this guy depends on n through this x here, integrate over momenta, and calculate what is this delta t, what is this ALM, and then take the average, and that will be your CLs, right? And there is a simple trick to do that, to relate this, to cast this in the form of, I mean, this is a horrible integral. That looks like a horrible integral. I remember in the beginning of 80s, when the machinery wasn't quite developed, we were studying the influence of gravitational waves on the temperature of cosmic microwave background, and we were stuck with this integral for a long time. Nowadays it's all very simple, but we didn't quite know what to do with that, and it was a lot of effort to calculate even quadrupole anisotropy that we finally did. But nowadays, I mean, we didn't know this couple of simple tricks. Simple tricks are as follows. First of all, here you have this exponent e to the I n I k, let me write it this way, k eta naught, and the product of the unit vectors, one unit vector is directed along k, and another unit vector is our unit vector, direction to the sky, right? And then you know that this exponent is expressed as a sum of Legendre polynomials. This is sum over the L to L plus 1 imaginary unit, which is now GL, that's the key player, K eta naught times PL of N L prime, let me call it L prime, sum over L prime, N, K, N, N, okay, dot. So you expand the exponent, that's a very well-known expansion, expand the exponential thing here in terms of, let me write down minus sign here, or I guess I should put here plus I. Expand it in terms of the Legendre polynomial, and then you know that this Legendre polynomial presentation in terms of spherical harmonics, 2L plus 1, 4 pi over 2L plus 1, sum over M prime equal to minus L prime to L prime, Y LM L prime M prime of N, Y star L prime M prime of NK. Okay? Good. Right? This is the summation formula for Legendre polynomials or for spherical harmonics. You can check it. It's a very powerful formula. And therefore, immediately calculate the angular integral here, right? Because the spherical harmonics are orthonormal on a sphere. Okay? So what you're getting at is that it's a lengthy calculation, but let me still do it because the result is quite nice. You get for ALM the expression like this. ALM is, well, first of all, you have temperature T, because this is delta T over T. Then there is this remaining integral over dk, three-dimensional integral. Now 4 pi I to the L, JL. And these are GLs are spherical Bessel functions, right? You know this notation. This is spherical Bessel function, whose properties I will tell you immediately. K eta naught times this perturbation T SW times zeta of K, and you have remaining spherical harmonic Lm of Nk. So there remains only the integral of momenta, and I think it's time to tell you what are the properties of the Bessel functions, spherical Bessel functions, which are in the heart of all calculations in this business. They're here. For L large enough, large meaning larger than 5 roughly, and even smaller, GL of K eta naught is essentially 0 if K et naught is less than L. L plus 1/2, in fact. Okay? Which tells you that long wavelengths do not contribute at all to high multiples. Right? And you understand why. Do you understand why? Well, in principle, it's clear that if you have very long wavelength modes, then you see them at large angles, right? And high multiples measure small angles. Now you can ask, what happens if my wave K is not perpendicular to my line of sight? What happens if this K, this mode goes at some angle to my line of sight? The answer is that it contributes to even longer, even larger angular scales. See, here is my surface of light scattering. I'm watching from there. Okay. Here is the wave at a given momentum k, right? So these are surfaces of constant phase, right? So you see the size here is bigger than this one. So this is wavelength, and this is bigger than the wavelength. So if the waves move at a certain angle to my line of sight, they contribute to larger angular scales, to even smaller multipoles, as compared to a wave of the same momentum, modulus of momentum moving normal to my line of sight. So that's why only modes of momenta higher than this typical scale L over, so K is less than L over eta naught. Only modes of momenta higher than this contribute to my perturbation. But not much higher, because this J goes roughly like 1 over K8, let me see, goes roughly like, well, it's 1 over L, and there is roughly the ratio of K eta naught over L, roughly, with oscillating cosine. I will tell about oscillating cosine later on. But so as you go to larger momentum, this term here drops down, right? And therefore, only momenta in this range, K roughly of order of L over eta naught, contribute to the perturbation at given L, to ALM at given L. Okay? So that's the origin of my claim that once you consider the multipoles L, then you're probing wavelength of this order, which is natural. It's just an angle that corresponds to the angle you see a given wavelength. If it's perpendicular, if it's not, then it's not so. But there are shorter modes that contribute, but their contribution drops down essentially because you have less and less phase space here. All right, with this understanding, you now calculate CLs, right? CL is just the average of square of this thing, right? And remember, my zeta has the property that its average is proportional to the delta function. Let me write this as 1 over 4 pi k cube p zeta of k times delta k plus k prime. You plug this in here, take square, and in the end you get the following formula that CL, which is 1 over L to L plus 1, is given by an integral, is t squared 4 pi integral of GL after you. The integral over this YLM is again trivial. It's it gives you, as promised, the integral over nk of YLM. That's the technical reason why you get delta symbol L prime n prime of nk integrated over angles in the momentum space now gives you indeed 1 over 4 pi delta m prime delta LL prime. So I was not cheating by saying, when I was saying that this A, the average values of A times A is proportional to delta symbols. That's the property of spherical symmetry of your system. So altogether I get this GL squared of K eta naught, and the transfer function squared, and dk d3k over 4 pi k cube p zeta. That's a simple formula. Okay, if my transfer function is constant, which is true for low multiples, then this is just an integral over this is one-dimensional integral now. Okay, and this is one-dimensional integral, just an integral over this variable here. And remember, I have 1 over L here and integral over this thing here. So altogether, this will give me something which is t squared times constant over L squared. Okay, times p zeta at L over eta naught. Okay, good. So this means that what is shown here is actually not CL. What people are usually show is not CL. It's the combination DL, which is equal to L times L plus 1 over 2 pi CL. Okay, so CL themselves are inversely proportional to L squared, so DL is flat, and this is the case. Here is this Sachs-Wolf region with dominating Sachs-Wolf effect and superhorizon modes by recombination. So all these parts, all these modes are superhorizon at recombination, and as we see, they give flat contribution, flat in essentially independent of L contribution to the angular spectrum of cosmic microwave background. Right, now let me be quicker. Next point is to go to higher multiples, and this formula remains correct. But the point now is that this transfer function t, here is actually pretty complicated, right? So let me write down the Sachs-Wolf contribution again. Here it is. Okay, remember, this term here had also an oscillatory part, right? So if we're sticking to the Sachs-Wolf effect, the first term here, which is dominant, by the way, why is it dominant? At low multiples, velocities are small, as we saw, right? That correspond to low momenta, and velocities are small. So this term is small at low multiples. At higher multiples, it is small because you need modes which are going towards me or away from me, and the effect is proportional to the angle of this wave of momentum k the angle, the cosine of this angle here. Okay, so you need waves that travel towards me basically, and this gives me small phase volume. So numerically you get suppression always for Doppler effect. Now integrated Sachs-Wolf effect is also small because most of the time my recombination occurred when I'm almost at the radiation domination epoch, and then there is radiation meta-domination epoch, and meta-domination epoch continues until very recently, and therefore at meta-domination we remember that these gravitational potentials stay constant. They are independent of time, right? That we derived. So gravitational potentials stay constant, and since they are independent of time, the contribution here is small, right? The contribution here comes from to the integrated Sachs-Wolfe effect. It comes from the time near recombination, okay? That corresponds to the multipoles in this range here, because at that time we're still not quite at matter-dominated epoch. There is some contribution of radiation to energy density, so it's not quite matter-domination. And also there is contribution of Sachs-Wolfe effect, integrated Sachs-Wolfe effect, at low multipoles, which corresponds to today, basically, a very recent epoch in the universe, when we are starting to feel dark energy. So this, green line is a prediction, and the fact that it goes upwards here is the effect of dark energy. Right? This is integrated Sachs-Wolfe effect at low multipoles due to dark energy. Okay? When again, it's not matter domination and the gravitational potential vary in time. Okay? So the Sachs-Wolfe, roughly speaking, is dominating, but other effects, with the precision we are having data now, the other effects are, of course, important. Okay, now back to Sachs-Wolfe effect here. So here I have oscillatory factor, right? Which yielded also the baryon acoustic oscillations, as we discussed yesterday. And also a constant factor. And constant factor is due to the fact that there is a constant or slowly varying with momentum factor, which is due to the fact that you have a dark matter, and perturbations in dark matter density induce dark matter potentials. Now back to your homework. If I had only photons, what would be this sum? I gave you homework yesterday, right? Didn't I? What is this sum for pure photonic gas? Zero. Isn't that obvious? Come on, you have potential wells, and suppose you are asymptotically flat. We are sitting somewhere here. You have potential wells. My system is in thermal equilibrium, right? So photons coming from here to here, and from there to here, from potential well, potential hill to here, should be all the same when emitted, when received, right? It's thermal equilibrium. You can exchange your photons freely, and you don't change your system, right? So all the photons coming from here are no different from the photons coming from there to one and the same point, right? Agreed? That's thermal equilibrium. So this term is zero for pure photon gas. Now, the second part of homework was, what is it if we had baryons? Well, that part of homework you haven't done, obviously. But that's easy. That's trivial. Let's take this equation here, this one, our conservation equation, applied to baryon photon component. Okay, delta P is the pressure in photons only, right? So let me write it down. 1/3. Velocity is 0. We're talking about static potential phi. What sort of energy density variation will it induce? That's what's my question. So I apply this equation here to the baryon photon component, and this phi is a source which is due to dark matter, right? So here, the first term is 0 since my source is static. Delta P is 1/3 of photon energy density. There is no pressure due to baryons. Now these two terms vanish, right, because we are static. So what we have here is plus P plus rho, which is P gamma, 1/3 of rho gamma, plus rho, and rho has rho gamma plus rho baryons times phi equals 0. Okay? That's our conservation equation for static potential, no velocity, no anisotropic stress here. Okay? That's it, because then my delta rho gamma, delta rho gamma, here's this, delta P is delta rho gamma, 1/3 of delta rho. My delta rho gamma divided by rho gamma equals, as promised, yeah, this is 4/3, right, 4 minus 4 phi, as promised. For pure photon gas, this will be minus 4 phi, and there will be cancellation, complete cancellation in this constant part, a non-oscillating part of Sachs-Wolf effect. And then there is this term here, which is plus 3 rho baryons over 4 rho gamma times phi. Okay? And this is delta gamma. So my integrated Sachs-Wolf, my Sachs-Wolf effect, 1/4 of rho gamma plus phi, contains oscillating part, cosine sound horizon times k, oscillating part with momentum, and non-oscillating part, which I think I have. So this is a non-oscillating part, which is proportional to the baryon density, right, divided by photon density. And I think I have shown that there is 1 over k squared term, eta equilibrium k squared term in the potential, and all this is multiplies 1 the same random field zeta. Okay, where A and B are some slowly varying functions of momentum. So that's basically what it is. Okay, so I have a term which slowly, I'm talking about higher multiples, it decays at larger k, and therefore it decays at higher multiples, and then there is an oscillating term with slow variation of amplitude as a function of momentum. Okay? Right, so these two terms, being this sum being averaged, becomes oscillatory function, right? Furthermore, it is oscillatory function of momentum, and as we discussed, there is this relationship that L is k over 8 naught. So these are the entire thing here will become oscillatory function of entire thing here. This is essentially the transfer function. It's an oscillatory function of momentum, and therefore oscillatory function of L. And with this identification, you can understand what the corresponding L's are, right? You have to have this cosine either plus or minus. And furthermore, depending on the sign here, there is constructive or destructive interference. And that's precisely what we see in this nice figure, right? So first of all, there is overall decline. This decline is due to 1 over k squared, basically. Now, the heights of these peaks are actually decreasing because of dissipation effects. The most important is so-called silk effect. It's not, I mean, beyond the scope. But there is a, you see, kind of constructive interference here, interference here, and destructive interference there, right? So if you consider these peaks as as peaks over the decreasing function, then obviously this one is lower than that one, right? So we see by naked eye this destructive interference and constructive interference for the odd peaks. Okay? So that's basically explanation of what we see in this figure. Okay? You can qualitatively understand what's going on. Here we have flat due to the fact that my modes are outside the horizon yet. Here I have oscillating acoustic waves, and these oscillating acoustic waves produce acoustic peaks in the temperature and isotropy. By the way, let me here these are the three contributions. This is main contribution Sachs-Wolf effect. This is the integrated Sachs-Wolf effect. As promised, it's sizable at multiples corresponding to the recombination epoch itself and large multiples corresponding to present epoch. And this is Doppler effect, which is somewhat suppressed, somewhat smaller than the main Sachs-Wolf effect. Okay. Now, what do we learn from all that? Well, of course, we learn a lot of things. First of all this discussion, all these cosines would not be there if my modes were not superhorizon, if they were created later on. Why this is cosine and not cosine with arbitrary phase? Because I started off superhorizon. I had only one solution in the superhorizon regime, remember. We discarded the decaying mode. There was only constant mode. Therefore, the phase of this cosine is fixed. It's not a combination of waves with different phases. It's one the same phase for everybody. And this is due to the fact that I was assuming that my modes were superhorizon. And the fact that I see the oscillatory pattern tells me that my modes were superhorizon. I said in the beginning of the lectures that the very fact that I have perturbations at very large angular scales, they are superhorizon to large angular scales, this very fact already tells me that the modes are superhorizon. But these were also superhorizon because they started off with one and the same phase. If you want to do something different, if you want to create the perturbations by using topological defects, for example, at the hot stage, then there is no reason whatsoever to have one and the same phase for all the modes, and that's what's shown here. These are calculations done in various topological defect models of cosmic microwave background and isotropy, and you see there is no oscillatory pattern whatsoever. So the very fact that we have oscillations means that the perturbations were created before the hot epoch. Now, this picture tells you that we are dealing with adiabatic perturbations because the initial conditions for entropy perturbations, as we discussed, are completely different, and therefore their evolution will lead to different pattern, and that illustrates the point. So at the place where you have a peak in the, say, in the adiabatic perturbations case, you have a dip, in fact, in the entropy perturbations. So they're completely different, and therefore one can place rather strong bounds on a mixture of entropy perturbations. All right? We also know that baryons make a strong effect. This term here is just proportional to the baryon mass density, or baryon to photon ratio, if you like. And therefore, if you vary a little bit your baryon to photon ratio, you change the picture. That's shown here. You vary by a factor of 10, you get completely different, height of the peak. And height of the peak is an interference between these two terms. Okay? So you measure Very. So with this understanding, you understand that the main contribution of gravitational waves will come from at low multiples, right? Low momenta, low multiples. Once you go to higher multiples, the contribution of gravity waves is small, is getting smaller and smaller. So by looking at this range here and comparing it with what's going on here, you figure out that everything is consistent with the fact that there is no contributions of gravitational waves or tensor perturbations to the temperature anisotropy of CMB. Everything is consistent with the fact that there's no gravity waves, and furthermore, you place relatively strong bounds, not very strong, but relatively strong bounds on the gravity waves, as I told you, on the order of 10% in terms of ratio of tensor to scalar spectrum, power spectrum. So that more or less completes the discussion of temperature of cosmic microwave background. And next time will be, I mean, that will be an interesting experience for me. I never gave a lecture on that, on the polarization of cosmic microwave background. We'll see how it goes. I'm not sure it's going to be simple discussion with at least some quantitative, qualitative, whatever, understanding of what is going on. I'll try. Okay.